Welcome to Lecture 2 for Meteorology, an invitation to the atmosphere, energy, warming the Earth, and the atmosphere. How do we warm the Earth? How do we warm the atmosphere? The obvious answer is the sun, but what are the processes involved in warming the Earth and the atmosphere?
We are going to study temperature and heat transfer, the energy balance, focusing on absorption, emission, and equilibrium, and incoming solar radiation, insolation. Temperature and heat, not the same thing. Kinetic energy is the energy associated with molecular motion. Now that is throughout all science. Kinetic energy is referring to energy associated with molecular motion. Temperature is a measure of average kinetic energy. So temperature is a human construct. I will say that many times in this class. Something that we created. We needed to understand. We constructed something. We called it temperature. Temperature is a measure of the average kinetic energy of molecules. So temperature is a measure of the average speed of molecules, where faster average speeds correspond with higher temperatures. In the illustration, cold air and warm air. Now let's look at what we see here. We see a bunch of little molecules. There's all diatomic, meaning there's two molecules, two little greens stuck together, two little reds stuck together on both sides, and then swooshes, not Nike swooshes, but just swooshes behind the molecules. Well, the two molecules represent either nitrogen or oxygen. Nitrogen and oxygen are always diatomic in the atmosphere, meaning there's always two of them together. It's always O2 or N2. And the swooshes represent how fast they're moving. In the cold air, the swooshes are short. In the warm air, the swooshes are long. So in the cold air, they're moving more slowly. In the warm air, they're moving more quickly. And you'll notice that in cold air, the same number of molecules take up less space. In the warm air, the same number of molecules take up more space. So if we consider that red globe or that orange globe to be a parcel of air, that's a parcel of air. Now there's no such thing as a parcel of air in the real atmosphere. This is, again, another human construct. We're going to call that a parcel of air. The cold air with the same number of molecules compared to the warm air with the same number of molecules takes up less volume. If you have the same mass and less volume, then the air is more dense. It is more dense, whereas with the warm air, you have the same mass and more volume. The air is less dense. Less dense air will rise, warm air will rise.
As the temperature inside the jar decreases, the water vapor molecules move more slowly. And as the temperature increases, the water vapor molecules move more quickly.
Density and temperature. Warm air molecules move faster and further apart. The same mass, more volume, less dense. So again, we talked about density in chapter 1. Rho, density equals mass divided by volume. Cold air molecules move slower and closer together. The same mass and less volume. Density equals mass over volume. It's more dense. So what's changing in our mathematical equation? D equals m over v. Well, mass is not changing. It's remaining the same. But if volume increases in the warm air, then density by mathematical calculation is lower. It's less dense and warm air rises. If mass remains the same, but volume goes down, it's less volume, then that lower volume number goes into the same mass number more times. Density is higher, it's more dense. Cold air sinks, warm air rises. If you have an environment or the atmosphere with a cold parcel, it will sink, and a warm parcel will rise. Temperature scales, again, a human construct. You have Celsius and Fahrenheit and Kelvin, all named after scientists who set these scales in place. Thermometers on the right show you those scales with Celsius in the middle. Celsius probably making more sense. Setting 0 at the freezing point or melting point of water at sea level, and 100 being the boiling point of pure water at sea level. That's the Celsius scale. Nice 10-unit divisions. And much like the metric system. Makes a little bit more sense. But of course, in this country, we still use Fahrenheit, where 32 is the freezing point or the melting point, depending on which way you're moving, and 212 is the boiling point. Now, Kelvin is a whole different thing. Kelvin, 0 is absolute zero. At absolute zero, you are at the lowest temperature possible, and molecular motion ceases. When we talk about absolute zero, we're talking about no molecular motion. Remember, temperature is a measure of molecular motion, the speed of molecules. So absolute zero, or 0 degrees Kelvin, is absolute zero, zero molecular motion. Temperature and heat. Temperature is the measure of the average speed of molecules. Heat is energy being transferred from one object to another because of the temperature differences between objects. And heat moves from higher temperatures to lower temperatures. So temperature and heat are not the same thing. The temperature is the average speed of molecules. Heat is energy being transferred from one object to another because of the temperature differences between those objects. Heat always moves from higher temperature to lower temperature. So place your hand on the desk or the table in front of you, and you know that it's cold. And you know that your body is 98 degrees or somewhere around that range, and that desk feels cold. And that's because heat is moving from your hand into the desk. It's moving from a higher temperature to a lower temperature. And you feel it as being cold because it's pulling the heat out of your body. If you grabbed a very hot object, you'd feel it as being hot because that hot object is moving energy into your body. It's going from hot to cold into your body. So you feel the heat. Temperature and heat are not the same thing. How is heat transferred? Well, it's transferred through conduction, convection, and radiation. And this first slide illustrates conduction. And we've got a neat little picture show movie going on there where the first molecule on the lower left-hand side is heated. And how is the rest of the object, or how is the rest of that substance heated up? It's heated through conduction, transfer of heat from molecule to molecule. The first molecule begins to move more quickly. If it's a solid, it may just be vibrating or rotating more quickly. If it's a liquid, it may be moving through the liquid more quickly. If it's a gas, it may be zipping around in the atmosphere more quickly. How does it heat the other molecules? By conduction, through physical contact. The faster motion, the faster wiggling then causes the other molecules to wiggle. So in order to heat by conduction, there has to be contact, which means this happens best in a solid, not so bad in a liquid, and not so good at all in a gas. Energy absorbed by heat sources causes molecules to vibrate more quickly, which in turn causes adjoining molecules to vibrate faster. Faster motion equals higher temperature. Heat transfer. How is heat transferred in different objects? Well, it's transferred differently in different objects, and the degree to which it's transferred is known as heat conductivity. Here's a table on heat conductivity of different objects, and you can see that still air or wood transfers heat very poorly, where granite, iron, and silver transfer heat very, very easily, very, very quickly. So let's take an illustration. Let's say you have a wooden pole and you stick one end of it in a fire. Let's say it's 6 feet long. Will you ever feel the heat at the end that you're holding? If one end goes in the fire, you're holding the other end. Will you ever feel that heat? Will heat ever be conducted up that wooden pole? No, it may catch fire and burn, but the heat's not going to be conducted. Whereas if you had the same pole made of iron or silver and you stuck that in the fire, yes, in the case of iron, eventually the heat would conduct up the pole. And in the case of silver, it happened actually much, much more quickly as well. Going back to wood, you go to the convenience store, you buy a can of a frosty cold beverage. The convenience store clerk may place that beverage in a paper bag, a small paper bag. Are they doing that so no one around you can see what's in that bag? No, they're doing that so the thermal conductivity, the low thermal conductivity of paper, remember paper is made of wood, will help keep that frosty cold beverage cold. You put a cold beverage in a paper bag, to help keep it cold. Wrap it in a napkin to help keep it cold. And then other objects in between, dry soil and water and snow and ice, they all conduct temperature differently. Heat transfer by convection. Convection is the transfer of heat by mass movement, meaning you heat up a mass, liquid or gas, you heat up that mass, and then you transfer it to a different place, and that's convection. Convection in the atmosphere and in liquids refers to the up and down movement of heat transferred by mass motion. So convection occurs in liquids and gases because they flow freely. In the atmosphere, convection is thermally driven vertical motion, up and down, both upward and downward. Advection, not convection, advection is the horizontal motion of air. And that, that's basically the wind. Conservation of mass. What are we talking about here? In our picture on the left-hand side, we see that air, that mass of air at the surface, is heated up at 2 o'clock in the afternoon by the hot sun. As it becomes less dense, it heats up, the motion becomes faster. Faster molecular motion takes up more space, same mass, less dense, it begins to rise. As it begins to rise, that mass is moved away. Well, nature does not like a vacuum. Whenever you evacuate mass from one spot to another, nature wants to replace that mass. Nature abhors a vacuum. Nature does not like a vacuum. So we've taken that warm mass of air at 2 o'clock, lifted it up, we've evacuated it, upward vertical motion. So nature, the atmosphere, wants to replace it, and it replaces it horizontally from the side. That cool air comes in from the side. That is the advection. As that warm air continues to rise, it eventually will cool higher in the atmosphere and also begin to sink down, and that's where you get your complete convection cell of up and down. And there's your convection cell. Hot surface in the middle, air is rising, it goes up, it cools, winds move it away, and it begins to sink. It sinks because it's cooler, so it's going down. That's also a convection, the downward motion of the cooler air. And then it moves into the surface, at the surface, and that's the advection, or the wind. So convection up and down, hot air goes up, and then as it sinks out on either side, it moves inward. That is the wind. The wind doesn't move it inward. It's the cold and the hot, the difference between the two causing it to move inward. That's the wind blowing, and that's your convection cell. Heat transfer by radiation, quite a bit more complicated, so we'll talk a little bit more about that. Radiation is the transfer of energy from one object to another by radiant energy without the space in between being heated. All right, so radiation. All objects emit radiation. You and I are emitting thermal radiation. We are also having radiation reflected off of us in the form of visible light, the colors that we see of our clothes and our skin and our hair and our eyes. So all objects emit radiation. And radiation is the transfer of that energy from one object to another without the space in between being heated. So if I have a hot object on one side of the room and I feel the heat of that object on my side of the room, the air in between is not being heated. I'm feeling the radiant energy that is being absorbed by my body. Radiation travels in waves that release energy when they are absorbed by an object. So with the case of the sun, we know that space is very, very cold, right? Space is freezing cold. Astronauts have to be protected. But the sun emits radiation that warms the Earth in a significant manner, but the space in between is not warm. That's because the sun's energy is being transferred by radiation, and the space in between is not warmed. Until the Earth actually absorbs the radiation of the sun, it does not warm up. Once it does warm up, it warms the atmosphere around it, and we have a warm day, sunny day, but the space in between is not warmed. The waves of radiation have both electrical and magnetic properties. So they're called electromagnetic waves. Radiation is an electromagnetic wave, the EM spectrum, electromagnetic. Electromagnetic and those different properties, probably a conversation for your physics class. Electromagnetic waves do not need a medium to propagate, and they move at light speed, the speed of light. All matter emits and absorbs radiation. Now let me go back up to the bullet point above. Waves do not need a medium to propagate. theoretically, there is nothing in space. It's complete vacuum or void. Yes, there's some dust, there's some gas, but the molecules are so far apart that essentially it's a vacuum. So the electromagnetic radiation of the sun does not need a medium to move. It moves through space. It moves through a vacuum. And when we absorb it here on Earth, that's when we warm up. All matter, as I said, emits and absorbs radiation. The wavelength of the waves, all these waves I'm talking about, these electromagnetic waves, they look like a sine wave, just a typical wave up and down. The wavelength is the distance along the wave from one crest to the next. And wavelength of radiation is going to become very important to us, where short wavelengths represent high radiation and higher temperatures, and longer wavelengths represent lower amounts of radiation. Radiation with longer wavelengths carries less energy than radiation with shorter wavelengths. Short wavelengths carry a great deal of energy. Long wavelengths carry much, much less energy. The sun's radiation comes in very short wavelengths. The sun's radiation carrying lots of energy. So here's an illustration of that fact. We start with AM radio waves, and we work our way down through infrared, and ultimately down to X-rays. Remember the X-ray gun in the science fiction movies? Okay, the old science fiction movies. That's where all the energy is carried. That's why they're so dangerous. Very, very short waves carry much higher amounts of energy. Visible light, the white light of the sun, carries more energy than infrared. Now, infrared refers to temperature. Think about infrared goggles. They see temperature at night. Visible light carries more energy. Ultraviolet even more than the visible. So when you put your sunscreen on, what are you protecting yourself from? Are you protecting yourself from the warmth of the sun or the white light of the sun? No, you're protecting yourself from the ultraviolet waves or rays of the sun, because those shorter wavelengths carry more energy. Now, some complicated equations, not equations that you'll have to memorize or have to be able to solve, but they talk about two different concepts of radiation that you do need to understand. The wavelength of maximum emission of any body is inversely proportional to its absolute temperature. Thus, the higher the temperature, the shorter the wavelength of maximum emission. This phenomenon is also called Wien's law. The following equation describes that law. The wavelength of maximum emission is equal to a constant divided by the temperature. So as the temperature goes up, the wavelength of maximum emission goes down. It's a shorter wavelength. As the temperature goes down, cooler temperatures, the wavelength of maximum emission will then go up. Longer wavelengths carry lower temperatures. So what is the wavelength of maximum emission? All bodies, all objects emit radiation, but they emit different types of radiation. The sun, it will emit short-wave radiation, some long-wave radiation, and a whole lot in between. It emits gamma rays and X-rays, but it also emits radio waves. It also emits infrared radiation and white light. But where does it emit the most radiation? At what wavelength does it have its maximum emission? So any body's, any object's maximum emission comes at a specific wavelength. And that wavelength can be determined by this equation, where temperature and the wavelength of maximum emission are inversely proportional. The higher the temperature, the shorter the wavelength. The higher the temperature, the shorter the wavelength. The sun is very hot and has a very short wavelength of maximum emission, where the Earth is much cooler and therefore has a much longer wavelength of maximum emission. The amount of electromagnetic radiation emitted by a body is directly related. Now here's a second aspect. The amount of electromagnetic radiation emitted by a body is directly related to its temperature. So not the wavelength of maximum emission, but here the second aspect is the amount, how much electromagnetic radiation is emitted by a body. It's directly related to that body's temperature. If a body is a perfect emitter, a black body, the amount of radiation given off is proportional to the fourth power of its temperature as measured in Kelvin units. This natural phenomenon is described by the Stefan-Boltzmann law. Stefan and Boltzmann being two scientists. The following simple equation describes this law. E, the energy, the amount of energy, is equal to sigma, which is just a constant, times the temperature raised to the fourth power. So as that temperature goes up, the amount of radiation that's emitted goes up to the fourth power. It goes up in massive amounts. So as temperature goes up, the amount of radiation, the amount of energy given off by an object goes up very, very rapidly. So again, the Earth is cool compared to the sun, so the Earth gives off a small amount of radiation where the sun gives off a tremendous amount of radiation. So what do you need to remember? What do you need to write down? Absolutely. Both the wavelength of maximum emission and the amount of electromagnetic radiation of energy are proportional to the temperature of the object. The wavelength of maximum emission inversely proportional, and the amount of energy directly proportional. Wien's law tells us the sun is hot, about 6,000 degrees Kelvin. Then the wavelength of its emitted radiation will be short and lies within the visible spectrum of the electromagnetic spectrum. Solar radiation is referred to as short-wave radiation or incoming short-wave radiation, and sometimes insolation. So Wien's law, the first law, tells us that if the sun is hot, 6,000 degrees Kelvin, then the wavelength of its emitted radiation will be short, right there in that visible spectrum. Solar radiation is referred to as short-wave radiation or incoming short-wave radiation, sometimes insolation. I'll refer to it a lot as insolation. So look at the graph here. The y-axis, radiation intensity, how much, okay, and the x-axis is the wavelength. So when you look at the sun's radiation, it goes up very, very high. The amount goes up very, very high in that visible light spectrum, 0.4 to 0.7 micrometers. That is the visible spectrum. That's the spectrum of visible light, starting with the purples, very close to ultraviolet, going through your blues, your greens, your yellows, your oranges, and your red, to the infrared spectrum. So that's where you get those two words, ultraviolet and infrared. The sun's maximum wavelength, maximum emission, where it emits most of its wavelength of radiation, is in that visible spectrum, 44%. Then 37% in near infrared, 11% in far infrared, less than 1% for all those others that are much longer, and about 7% in that ultraviolet spectrum. So that is the sun's shortwave radiation, insolation, incoming shortwave radiation. Conversely, Wien's law also tells us since the Earth is cool, then the wavelength of its emitted radiation will be long and lies within the infrared spectrum. So this is the Earth compared to the sun. On the left is the sun, 0.4 to 0.7. That's where our wavelength maximum is, with that 6,000 degrees Kelvin, where the Earth's radiation is mainly between 5 to 15 micrometers. So the sun's radiation is short-wave radiation, and the Earth's radiation is long-wave radiation. Earth's radiation is referred to as terrestrial long-wave radiation, or sometimes outgoing long-wave radiation. Bottom line is, the sun emits short-wave radiation, the Earth emits long-wave radiation. This will become very important as we talk about the greenhouse effect. So let's talk about it. An object that perfectly absorbs and emits radiation is referred to as a black body, and both the Earth and the sun are black bodies. And really, most objects and substances are black bodies. Not all, because you're going to find out. Some don't absorb and emit perfectly, and those are called selective absorbers. So the atmosphere is not a black body. It is not a black body. It absorbs some wavelengths in the infrared range, but it's transparent to other wavelengths in the visible range. Gases in the atmosphere are selective absorbers. They only absorb and then re-emit at certain wavelengths. So take a look at that figure. Now we have 1, 2, 3, 4, 5, 6 graphs. The top 5 are separate gases, and the bottom one is a combination of all the gases. So nitrous oxide, it absorbs and re-emits only in the longest wavelengths, okay? So 5 to 10. All the visible light of the sun and the infrared energy of the sun passes right through nitrous. It never absorbs it. Methane is also not absorbed by the visible or infrared radiation of the sun. Now we start talking about molecular oxygen, both O2 and O3. They are somewhat better absorbers of incoming solar radiation. Then you look at water vapor. It doesn't it doesn't absorb any that comes in, but it absorbs a lot that goes out, those longer waves. And same thing with carbon dioxide. Nothing that comes in is absorbed by carbon dioxide, but a great deal more is absorbed by the outgoing terrestrial radiation. So the bottom graph is a combination of all that. And what that tells us that where the sun emits most of its radiation in that visible wavelength and in the infrared wavelengths, very little of that radiation is absorbed by the atmosphere. But as the Earth readmits the longer wavelengths, a great deal of that longer wave radiation, the infrared radiation, is absorbed by the atmosphere. And that's what keeps our atmosphere warm, and that is the greenhouse effect. So bullet point 4, the sun's incoming shortwave radiation, insolation, passes through the atmosphere and is absorbed by the Earth. The Earth, of course, is a black body, so it absorbs all the radiation and then readmits all that radiation, and it readmits it as a long wave radiation. Again, remember, lower temperature, longer wave radiation. The Earth emits long wave infrared radiation that is absorbed by gases, those selective absorbers. Those gases are then warmed, and they warm the air around them by conduction, and they also readmit long-wave radiation to be absorbed by other gases and the Earth. So most of the sun's incoming shortwave radiation goes right to the atmosphere and is not absorbed by the atmosphere. It is absorbed by the Earth, and the Earth warms up. As the Earth warms up, it readmits much longer wave radiation, and that longer wave radiation is absorbed by nitrous, methane, O2 and O3, water vapor and carbon dioxide. Those gases in the atmosphere, they warm up. They warm gases around them through conduction and convection, and they also readmit their long-wave radiation to other gases around them and back down to the Earth. The selective absorbers are nitrous, or methane, or O2 or O3, or water vapor and or carbon dioxide, of which water vapor and carbon dioxide are particularly effective, and water vapor, because of its abundance, is the most important greenhouse gas. Those selective absorbers are the greenhouse gases. As selective absorbers absorb and radiate infrared radiation, they are acting as an insulating layer around the Earth.
What the scientists here at Rother have discovered is that this part of Antarctica, the Antarctic Peninsula, is warming more rapidly than anywhere else on the planet. And after years of study, they think the answer to that lies down in the ice underground. I'm climbing down into a crevasse, and it's by getting down into the ice and drilling into it that scientists are able to build up a picture of the greenhouse gases that have been building up in our atmosphere. They find bubbles like this trapped in the ice and analyze the air inside them. This is air from many years ago. And in fact, they now have a record of the atmosphere stretching back 800,000 years. So this cave may to you and I look like a fantastic place of beauty, but for climate scientists, it's a treasure trove of key information. The ice reveals that the greenhouse gas, carbon dioxide, is now at unprecedented levels, and all around are the signs of melting.
Some of the glaciers are getting steeper. They're retreating back away from the sea, having to... some glaciers you can actually walk along beaches and what have you at the base of the glaciers, where in the past they were ice cliffs falling into the sea. So we do know that, the topography is changing, most likely as a result of its warmer temperatures.
You are quite wanting a cup of tea shortly.
Yeah, it's tough work for the scientists out gathering samples of the ice. But they say that for the first time their research has established a direct link between man-made greenhouse gases and the warming of this distant land.
So how does that look? The picture on the left is no atmosphere. The picture on the right is the atmosphere as it is now. On the left, the sun's incoming shortwave radiation is absorbed by the Earth, and then it's re-radiated as outgoing infrared radiation. Without the greenhouse gases, the average temperature of the Earth is calculated to be about 18 degrees below 0 Celsius or 0 degrees Fahrenheit, so well below freezing, no liquid water. That's without the selective absorbers of the atmosphere. With the selective absorbers of the atmosphere, this carbon dioxide, the methane, the nitrous, the oxygen and the ozone, and the water vapor being the most important, with those selective absorbers, the sun's incoming shortwave radiation passes through the atmosphere, is absorbed by the Earth. Earth warms up and radiates away its long-wave radiation. That long-wave radiation is absorbed by the atmosphere, warms the atmosphere, and readmits radiation out to both the atmosphere and the Earth. And that keeps the Earth's temperature at an average of about 59 to 60 degrees Fahrenheit and warm enough for liquid water. So that is the greenhouse effect, and that is our energy balance. If absorbed insolation and emitted terrestrial radiation are in balance and the Earth has reached what's called its radiative equilibrium, about 255 degrees Kelvin. The difference between the 255 Kelvin, 0 degrees Fahrenheit, and the 288 degrees Kelvin, 59 degrees Fahrenheit, that is the actual temperature of the Earth, is because of the selective absorbers, and that is the greenhouse effect. Warming from below. The Earth's atmosphere is warm from below. The atmosphere does not readily absorb shortwave radiation. The atmosphere is a window to the shortwave radiation of the sun, the incoming solar radiation, the insolation. Insolation passes through the atmosphere to strike the Earth's surface, warming the surface. So the sun's incoming solar radiation, insolation passes through the atmosphere, strikes the Earth warms up. Air molecules in the first few centimeters are warmed by conduction. So literally 1, 2, 3 centimeters of air close to the Earth are warmed by conduction. As warm air rises and becomes less dense, as it becomes less dense and rises, heat transferred by convection also warms the air above it. And then, of course, radiation radiates long-wave radiation of the Earth to be absorbed by those selective absorbers. So the atmosphere is not heated from above. It's literally heated from below. First, the Earth has to heat up, and then the atmosphere heats up the first few centimeters by conduction, then the rest of the atmosphere by convection and radiation. So that's why a cloudy day is a cooler day. The sun's shortwave radiation can't reach the Earth for the Earth to heat up. And a bright sunny day, of course, you know it's going to be hotter. So what happens to incoming solar radiation? This is that energy balance. 51% of the sun's incoming solar radiation gets to the surface and is absorbed by the Earth. About 19% is absorbed by the atmosphere and clouds. So a little bit of the shortwave radiation is absorbed. That's what's absorbed. Some of the radiation is actually scattered, and the rest of that radiation is reflected. Scattered radiation means radiant energy strikes an object and is deflected in all directions. So you can see in the picture the two molecules there, diatomic nitrogen or oxygen. The incoming solar radiation, that white light that's coming in, when it strikes that molecule, some of it is absorbed, tiny amount, 19%. The rest of it goes through that molecule right to the Earth at 51%. But a small amount of it is scattered. Radiant energy strikes an object and is deflected in all directions. And you can see the molecule, because it's about the right size, sort of breaks up that white light into its component colors. And because mostly it scatters the blues and the greens, that is the reason why the sky is blue. Some of that energy, however, is also reflected. Reflection is when radiant energy is turned backwards, so straight back from the object. So reflection, just like reflection in a mirror. So incoming solar radiation enters the atmosphere. 51% of it passes right through the molecules and is absorbed by the Earth. About 19% is absorbed by the atmosphere and the clouds. Some of it's scattered and some of it's reflected. The size of air molecules favors the scattering of those shorter wavelengths, violet, green, and blue, and that is why the sky is blue. So if you're standing directly under the noonday sun that white light travels literally through a short distance of the atmosphere. So very little blue light is scattered, and the sun and the sky appears much wider. Now, as the sun sets, or as it's coming up in the afternoon, in the morning, sunrise or sunset, you can see that the white light of the sun literally passes through a greater distance of the atmosphere. So as it's closer to noontime, 9, 10, 11 o'clock in the morning, 1, 2, 3, 4 o'clock in the afternoon, you get the blue, because mostly the blues are scattered out. But early in the morning and then late in the afternoon, closer to sunrise, the blues are scattered out, and then the yellows and the reds begin to be scattered out. And that is why your sunrise and your sunset tend to look reddish, because more of the white light of the sun is being scattered by the atmosphere. All right, that reflection in the atmosphere is known as albedo. Albedo is the percentage of radiation returned from an object compared to the amount of radiation striking the object. Different substances have more and less albedo. Fresh snow, freshly fallen, crisp white snow reflects up to 95% of the sun's, that is, incoming solar radiation. So it's cold to have snow, but if you have fresh snow, it makes it even colder because most of the sunlight is reflected back to space. And again, that's another reason why you have to wear sunscreen when you're doing some springtime skiing, because all that reflected light can give you a sunburn. Thick clouds reflect a great deal of radiation as well, thinner clouds less, and you can see different substances and different planets reflect more or less of the sun's radiation. That's known as albedo, the amount that's reflected back. So here's your solar energy balance. 51% absorbed at the surface, 19% absorbed by atmosphere and clouds. About 30% is reflected and scattered. 4% may be reflected back, 20% reflected and scattered by clouds, and about 6% reflected and scattered by the actual atmosphere. All right, let's talk about the parcel theory. We talked about a parcel of air earlier. Let's talk about what happens to a parcel as it moves up and down in the atmosphere. The parcel theory tells us that as air rises, it cools. As air sinks, it warms. You know that because if you're at the base of a mountain, it's nice and sunny and warm, but as you go up the mountainside, it gets cooler. At the surface, air has the same temperature and pressure. As the parcel is lifted, air pressure outside the parcel decreases. Remember that from Lecture 1. As you go up in the atmosphere, there's less pressure. In order to maintain equilibrium, air molecules then push out on the parcel and it expands. So look at our picture. The warm air on the left is a small little parcel. As it goes up the mountainside, it literally expands. Why is it expanding? Because the pressure is lower. Lower pressure allows the parcel to expand. As the parcel expands, it requires some of the molecule's energy to do the expansion, causing the molecules to slow down. Well, slower moving molecules have a lower temperature. Remember, temperature is simply the measure of molecular motion. So as a parcel of air rises, it expands and it cools. As a parcel of air is then forced to sink, outside pressure increases. Remember, the pressure is highest at the surface, about 1,000 millibars. Outside pressure increases, so the parcel is made to be smaller. It's compressed. And as that parcel compresses, the molecules inside the parcel tend to speed up and they warm up. So as the air parcel sinks, the outside pressure increases, the parcel contracts, it compresses, causing the molecules to speed up and warm the parcel. Rising air cools, sinking air warms. Rising air cools by expansion, and sinking air warms by compression. Two very important concepts you'll see over and over again. Rising air cools by expansion, sinking air warms by compression. So here's the parcel theory in play. Air that is forced to rise will cool by expansion. Air that is forced to sink will warm by compression. This is known as an adiabatic process. The air inside that parcel cools up going up the mountainside, but no temperature change is occurring, meaning there's no heat being added or subtracted. Going up the mountainside, there's not a tray of ice sitting underneath that parcel that's cooling it off. It's cooling off simply by expansion. It's an adiabatic process. As the parcel comes down the mountainside, it warms by compression. There's no heat being added. There's no fire underneath that parcel warming up that parcel. It's warming without heat transfer. It's warming adiabatically by compression. Back to the annual energy budget of the planet. It tends to be in balance over time. The amount of energy gained and lost is not equal, however, at different points in the planet. At higher latitudes, you lose more energy than are gained, and low latitudes receive more energy than they lose. The balance is kept by a transfer of heat by weather systems. So look at the picture on the right. It's literally a picture from your book turned on its side, because I wanted to give you an idea of the Earth. Because right there in the middle is 0 degrees latitude, or the equator. At the equator, there is more incoming solar radiation arriving each day than outgoing terrestrial radiation leaving. There's more sunlight coming in than outgoing long-wave radiation going out. And so there's a surplus. Above 38 degrees north and below 38 degrees south, there is less incoming solar radiation than what's going out, and there's a deficit. If there were no changes, if there was no movement or transfer of heat by weather systems, then the equator would just continue to warm up and the poles would just continue to get colder. That doesn't happen because heat is transferred north and south by weather systems. How does this affect the change of the seasons? The seasons are regulated by the amount of insolation received at the Earth's surface. This is largely determined by the angle at which the sunlight strikes the surface. Insolation striking the Earth directly is more intense than insolation striking the Earth at an angle. At an angle, light is spread out over a larger surface area. Also, at an angle, the insolation must move or penetrate through a thicker layer of the atmosphere, and that radiation is attenuated. Simply, it's scattered, or it's absorbed, or it's reflected back. And so not as much of it reaches the Earth. So, number one to remember, the seasons are regulated by the amount of sunlight that arrives at the Earth's surface. The seasons are not regulated by the distance from the sun. The seasons are not regulated by anything other than how much sun gets to the surface. How much sun gets to the surface is largely determined by the angle at which the sun strikes the surface. You can see it for the bottom right picture. Closer to the equator, the sun comes in at much higher angles. It's a much more direct angle at the equator and in the lower latitudes. More sunlight strikes the Earth, it's warmer in the low latitudes. We know that. It's warmer to the south. In the higher latitudes, less sunlight reaches the Earth's surface, and therefore it's colder. And you can see illustrations of how direct sunlight makes more insolation arrive with the flashlight, and how the low sun angle, the sunlight has to pass through a greater amount of the Earth's atmosphere and is therefore attenuated or scattered. At a high sun angle, there's less atmosphere to travel through, and more of that sunlight reaches the Earth's surface. So how is the Earth's surface warmed? What makes it warmer or colder at the Earth's surface? It's simply a question of how much insolation has arrived at the surface, how much sunlight has arrived at the surface. The second factor regulating the seasons is the length of the time the sun shines every day, called the photoperiod. You know that it's longer in the summertime and less in the wintertime, and that's because of the angle of the Earth, the tilt on the axis. In the wintertime, we're tilted away from the sun, as you can see on the left side of the picture, and our days are shorter. In the summertime, we're tilted toward the sun, and our days are longer. Not only are our days longer in the summertime, but because we're tilted toward the sun, we have a higher angle of sunlight arriving at the Earth. Higher angle of sunlight and a longer day means more solar radiation at the Earth's surface in the summertime in the northern hemisphere and warmer conditions. The second factor regulating the season is the length of time the sun shines every day of the photoperiod. Summer days are longer, and the noon sun is higher in the sky due to the Earth's inclination of 23.5 degrees from perpendicular, and always points in the same direction. That's kind of a by the way. The sun always points in the same direction. Well, look at the axis in this picture, always pointing up and to the left. Where is it pointing? It's pointing toward Polaris, the North Star. Now, does it point toward Polaris because Polaris is special? No, that just happens to be where it's pointing at this time. Will it always point toward Polaris? Well, actually it won't. The Earth's tilt changes gradually over many, many thousands of years, and it also spins like a top. It spins around like a top. So no, we won't always be pointing to the exact same point in the universe, but of course that change happens over many thousands of years.
The seasons are caused by the Earth being tilted on its axis as it revolves around the sun. During the summer, the northern hemisphere is tilted toward the sun. Longer days and more direct sunlight produce warm summer weather. We can see in the lower figure that at 40 degrees north latitude on June the 21st, called the summer solstice, the sun rises in the northeast, reaches its highest position at noon, then sets in the northwest. On each successive day past the summer solstice, the noon sun is a little lower in the sky and daylight hours are a bit shorter. On September the 22nd, the autumnal equinox, days and nights are of equal length as the sun rises in the east and sets in the west. On December the 21st, called the winter solstice, the northern hemisphere is tilted away from the sun. This marks the day with the shortest daylight hours in the northern hemisphere. Shorter days and the lowest noon sun of the entire year produce cold winter weather. On each day past the winter solstice, daylight hours increase and the noon sun is a bit higher in the sky. On March the 20th, the vernal equinox, days and nights are of equal length. And in another 3 months, once again, it's summer as the northern hemisphere is tilted toward the sun.
The last impact, the lowest impact on the seasons is the distance from the sun. Now look at this. In January, we're 147 million kilometers, and in July, we're 152 million kilometers. So we're literally closer to the sun in our winter time. So this is a very good example that no, the distance from the sun does not contribute to the seasons. Does the distance from the sun regulate the seasons? No, it does not. When the Earth is at its perihelion in January and its aphelion in June, the angle of the sun and the photoperiod are still the primary regulators of the seasons. By the way, all other celestial bodies also travel in ellipses and have perihelions and aphelions. And this is an example of how that works, where at the North Pole, the sun is either right at the horizon or in the wintertime or slightly above the horizon in the summertime. And the further south you go into the middle latitudes and then eventually to the equator, you can see how the sun is much, much higher in the sky. So in December, when at the North Pole the sun is right at the horizon and you have 6 months of winter, at that same time of year at the equator, you can see how the sun is much, much higher in the sky, and we have much more direct light, and therefore it is warmer. Here are some of those photo periods for different times of the year at different latitudes. And of course, in December and in June, we call those solstices, and then in autumn and in spring, we call those equinoxes. So the vernal equinox or the spring equinox arrives sometime around March 20th, not always exactly the same date. It's within about 24 or 36 hours. The summer solstice around June 21st, the longest day of the year, the autumnal equinox, again an equinox because as you can see from the chart, the days are 12 hours long and the nights are 12 hours long. That's about September 21st, and the winter solstice, the shortest day of the year, that is going to be around December 21st. All right. Let's move on to states of matter, and this becomes very important because we're also going to talk about how the change in state either releases or absorbs heat. So the three states of matter are solid, liquid, and gas. A gas is a substance that it can expand to fill any empty container. Atoms or molecules of gas are in high-speed motion and move in random directions. A liquid is a substance that flows freely in response to unbalanced forces but has a free upper surface. Think about a glass of water. There's always an upper surface. Otherwise, it takes the shape of the container, but there is going to be an upper surface. Atoms or molecules of liquid move freely past one another as individuals or small groups. Liquids compress only slightly under pressure. Of course, solids don't compress at all under pressure. Gases and liquids are both classified as fluids. So both gases and liquids are classified as fluids. That's why the atmosphere is a study of fluids, because both gases and liquids are classified as fluids because both substances flow easily. A solid is a substance that resists change of shape or volume. A solid can typically withstand stress without yielding permanently. A solid usually breaks suddenly. On Earth, water can occur in all three states, gas, liquid, and solid. What is important to us in the weather and understanding atmospheric sciences is what happens when water specifically changes from one state or one phase to another. So, latent heat, the release of latent heat or the absorption of latent heat. A change of state or a phase change, that is that transition between solid, liquid, and gas. All right? And that change of state or that change of phase typically occurs due to a change in temperature or pressure. In the atmosphere, mainly we're going to talk about temperature, but pressure can change the state of water as well. You can get vaporous water, water vapor, turning into liquid water droplets because of a change in pressure. That happens in the center of tornadoes where the pressure is extremely low. You get condensation as one of the reasons why you can see the tornado funnel. All right, latent heat. Latent heat is the heat energy required to change the phase of a substance. The amount of energy released or the amount of energy absorbed by a substance during a change of state without changing its temperature. Meaning when water goes from a gas to a liquid or from a liquid to a solid, that phase change happens and the water does not change temperature. It either releases heat or it absorbs heat during that phase change. Sensible heat is heat that we can actually feel or measure. So the latent heat of condensation is a warming process. The heat released when water vapor condenses to form liquid. And the latent heat of evaporation is a cooling process. The heat used to change liquid water into a vapor. So those are going to be the two important ones in the atmosphere. The latent heat of condensation is a warming process. When water vapor condenses to form a liquid, heat is released. The latent heat of evaporation is a cooling process. Heat is used to change liquid water into a vapor. To break liquid water molecules apart into vaporous water, you use heat, and it's a cooling process. The opposite occurs when condensation occurs. When vapor condenses into a liquid, that same heat is then released. All right, this is how it looks on a temperature scale. The x-axis is going to be heat in calories per gram. For every gram of water, it requires so many calories. And on the y-axis, we have temperature from 40 below to about 140. For water to evaporate, heat must be added to the water in a liquid state. After water reaches about 100 degrees Celsius, an input of 540 calories per gram is required to break the hydrogen bond and allow evaporation. So you heat up water to about 100 degrees Celsius, and at that point, without the water changing temperature, in order for the water to go from a liquid to a gas, you have to put about 540 calories per gram. That's a lot of energy to get it to evaporate. Well, the opposite is also true. For that water vapor to then condense into a liquid, you're going to release 540 calories per gram. That is the latent heat of condensation. That's the heat that's released when condensation occurs. The amount of energy required to break the bond is termed the latent heat of vaporization. When you're taking liquid water and you're breaking it down to create water vapor, the amount of energy required to break the bond is termed the latent heat of vaporization. Water has the highest latent heat of vaporization of any known substance. So here is another way to look at latent heat. On this picture, you have ice on the left, liquid water in the middle, and vapor on the right. To get water to go from a solid state, ice, to a liquid, and they get that liquid to go from a liquid state to a gaseous state or water vapor. From ice to liquid, you require 80 calories. From liquid to gas, you require 540 calories. Both of those processes are cooling processes. You take calories out of the atmosphere and put them into the substance to get the phase change to occur. You literally take 80 calories per gram out of the environment, put it into the ice to get the ice to go and turn into liquid water. Melting is a cooling process. Once it is liquid water, in order to get the liquid water to evaporate into a gas, you take about 540 calories, a whole bunch more, and put it into the water molecule to get the liquid water to turn into vaporous water, water vapor. And so evaporation is a cooling process. Condensation and freezing are the opposite. You have to remove 540 calories per gram of water to get water vapor to go into becoming a liquid. So you release that energy to the atmosphere. So condensation is a warming process. And believe it or not, even though it's a little counterintuitive, freezing is also a warming process, about 80 calories per gram. The term latent heat applies to the heat input that does not change the temperature but produces a change of state. The energy input or output associated with water and the three states of matter. We must add 80 calories of heat to change a gram of ice to liquid water. After the ice is melted, about 1 calorie of heat is needed to raise each gram of water by 1 degree Celsius. But 540 calories must be added to each gram of water to vaporize it, to boil it away. The process is the reverse for condensation and freezing. Here's just one more chart of that heat transfer that's taking place. Heat energy is being taken from the environment. It is a cooling process to melt or vaporize water. Heat energy is released to the environment to condense or freeze water. This is a detailed description of latent heat. Water molecules can move by rotation and vibration. Ice is not very free to move. Ice can vibrate, but ice remains rigid. Liquid water moves freely, but since the molecules are still very close together, they do not move as freely as water vapor. Solid water ice is the most ordered state of water, while gas is the least ordered state. In order for ice to go from ice to a liquid state, energy must be added to cause the ice to change from a higher state to a lower ordered state. When ice melts or water evaporates, energy must be taken from the environment in order for the ice or liquid to move to a less ordered state. Energy is needed to weaken the individual hydrogen bonds between water molecules. When water, in any of the three phases, moves from a higher to a lower ordered state, the air surrounding the water will have heat subtracted from it. The three processes that subtract heat from the surrounding air are evaporation, melting, and sublimation, the phase change from solid to gas. When water in any of the three phases moves from a lower to a higher ordered state, the air surrounding the water will have energy added to it. This is called a release of latent heat. When heat is subtracted from liquid water, the individual water molecule will slow down. They eventually slow down to a point at which the hydrogen bonds do not allow the liquid to rotate anymore. Ice now develops. The energy the water molecules once had to rotate has been given up to the surrounding air. The three processes that add heat to the surrounding air are condensation, freezing, and deposition, gas to a solid. Important. The process of evaporation and condensation take about 7.5 times as much energy as melting or freezing.
All right, this concludes Lecture 2, Energy, Warming the Earth and the Atmosphere. Our next lecture on Chapter 3 from the Introduction to Meteorology textbook is going to be on air temperature, and we'll see you then.